Let's talk about the chemical process of electrolysis. I wanted to try to write the simplest definition that I could, so here's what I came up with. Electrolysis is a process where electricity is used to make a chemical change happen that wouldn't happen otherwise. So we have some kind of a chemical change that doesn't happen on its own, but then we can use electricity to make that chemical change happen. Now, electrolysis is often used to take a compound and break it apart into the elements that make it up. We'll look at two examples of that in this video. First, we'll look at sodium chloride being broken apart by electrolysis into sodium metal and chlorine gas. And just FYI, this is an unbalanced equation. Then, we'll look at an example of water being broken apart using electrolysis into hydrogen gas and oxygen gas. So let's get started by taking a look at this reaction. So here's an unbalanced equation for the electrolysis of sodium chloride. Now sometimes people ask me, why is it Cl2 and not Cl? Well, that's because Cl, chlorine, is one of the diatomic elements. These are the diatomic elements. And the diatomic elements always form groups of two. They always pair up together. You never find just one of these atoms alone by itself. So this would never just be Cl, it would be Cl2 instead. So the equation that we've got here is an example of an oxidation-reduction reaction. Electrons are moving between atoms in this equation. I want to understand how they're moving and where they're moving. And in order to do that, we got to write oxidation numbers for the different elements in this equation. So check it out. I got some information here that will help us write oxidation numbers for these elements. We can do this really quick. So NaCl here is an ionic compound, sodium and chloride. Na is in group 1a, so it is always +1. Okay? Cl, chloride, is one of the halogens here, usually -1, positive with oxygen, definitely -1 here. And then on this side of the equation, we have sodium and chlorine on their own. They're elements by themselves. They're not bonded to any other elements. So Na over here is going to be 0, and Cl2 over here is going to be 0 as well. Okay, so those are the oxidation numbers for these elements. Now, to understand how the electrons move, we got to take a look at the changes in these oxidation numbers. We'll use this information to help us out. So let's take a look at sodium here, Na. On this side of the equation, it's +1, and then over here, it's 0. So its oxidation number goes down. So that means that it is undergoing reduction. It is gaining electrons. So sodium is reduced here from +1 to 0. And then Cl goes from -1 here to 0 over here. So its oxidation number is going up. It is undergoing oxidation, and it is losing electrons. It's being oxidized from -1 to 0. So sodium is reduced, gaining electrons, and chloride is oxidized, losing electrons. Now there's something really important about this process, and that's that this process doesn't happen on its own. Sodium chloride is also known as table salt, and you could keep table salt in your kitchen for hundreds of years, and it's never going to separate out into sodium and chlorine gas. It's just not going to happen. This process doesn't happen on its own by itself. To use chemistry terms, we can say that this process is not spontaneous. Spontaneous process is something that happens on its own. Now, a big part of the reason why this isn't a spontaneous reaction is because sodium and chloride over here are really happy with the number of electrons that they have. Sodium doesn't want to gain more electrons, and chloride here doesn't want to lose electrons. They're totally set right here. So we have to force this process to happen, and that's where the electricity part of electrolysis comes into play. The electrical energy from a battery can force this process to happen. So here's our battery. And a battery has these two sides, the positive and negative. The positive side of the battery pulls electrons in, and the negative side of the battery pushes electrons out. So these two things can force this process to happen. So chloride doesn't want to lose its electrons. But you know what? The positive side of the battery just pulls electrons away from it, right? It's like, you don't want to lose these electrons? Tough. I'm just going to pull them away from you. And the negative side of the battery that pushes electrons out, it's going to push electrons to sodium. Sodium doesn't want to gain electrons? Too bad. The negative side of the battery is going to push electrons to the sodium, making this process happen. So now, I want to show you the device that we use to do electrolysis and make this process happen. And then I want to use our atomic vision to see the atoms and electrons and how they move during this electrolysis process. So here's a picture of the device that we use to make this process happen. This is called an electrolytic cell, and it's got a couple of different parts. First, we got this container that's full of the sodium chloride. Then we got a battery, and the two sides of the battery are hooked up to what we call electrodes. The electrodes put electrons into the sodium chloride and they pull the electrons out. And then finally, the sodium chloride here, it's not just like the powdered table salt that you're used to from the kitchen. This has got to be molten, liquid, melted sodium chloride. Sodium chloride doesn't melt until about 1500 degrees Fahrenheit or 800 degrees Celsius. So it's got to be super, super hot. And this device has to withstand really high temperatures. The sodium chloride has got to be molten for the electrolysis to happen. Now let's zoom in on this a little bit more. If we could zoom in to the sodium chloride millions and millions of times, this is what we'd see. The sodium chloride is molten or liquid, which means that the sodium and the chloride ions have come apart from each other and they're in constant motion moving around in this container. Now, here are the electrodes. This is that one, and this is that one. These electrodes in the diagram here are way, way, way closer together than they should be based on this. This is definitely not to scale, but I wanted you to be able to see both of the electrodes. Now there's another important part of this electrolytic cell, and that is the battery. The diagram that I put here shows the direction that electrons move. Electrons move from here into the battery and then out of the battery into this electrode. So we can give names to these two electrodes based on how the electrons are moving, okay? The electrode over here we call the anode. The anode is the site of oxidation. Oxidation is happening in here because the anode is pulling in electrons, because this is the direction that the electrons move. Now over here we have the cathode. Reduction happens to the cathode. The cathode pushes out electrons because this is the direction that electrons are moving from the battery. So we got the anode and the cathode. We got the battery, the electrodes, and the sodium chloride. We're ready to do some electrolysis. I'm going to get rid of a few of these ions to make the process a little bit clearer. Okay, that's a little bit clearer. So now, we hook the battery up to the electrodes, and this is what happens. So this cathode here is connected to the negative side of the battery, so that means that it's going to have a negative charge. These positively charged sodium atoms are going to be attracted to the negatively charged cathode because opposite charges attract. So we got this Na plus moving over to the negatively charged cathode. And electrons, as we said, are being pushed out of the battery into the cathode. And this electron is going to be given to the Na plus ion. And gaining that electron is going to get rid of the charge on that Na. So it's going to turn this into a neutral sodium atom. The same thing is going to happen to this one over here. It's got a positive charge, it's attracted to the negative cathode, moves over here, an electron gets pushed from the battery, it goes into the sodium ion, and gaining that electron causes the sodium to lose its charge. So now we have two neutrally charged sodium atoms. Now over here at the anode, the opposite thing is going to happen. Electrons are going to be pulled out of these ions. So we got this chloride over here. It's attracted to the anode because the anode is hooked up to the positive side of the battery, and this is negatively charged, so it's going to be pulled over here. And the anode is pulling in electrons, so one of the electrons from the Cl- is going to be pulled up towards the battery, and that is going to cause the negative charge to go away because it's lost one of its electrons. And then over here, this Cl- is also going to get attracted to the anode. It's going to lose one of its electrons. It's going to get pulled up here towards the battery, and that is going to cause this to lose its negative charge. Now we said that chlorine here is one of the diatomic elements, so that means that we're never just going to find one of these atoms on their own. As soon as they don't have a charge anymore, they're going to pair up to form a Cl2 molecule. This is gas, and it's actually going to float away. So that's how the electrons move in this electrolytic cell. Here's a diagram of the process that I just showed you. I want to use this to write half reactions for what's going on at the anode and the cathode. So oxidation happens at the anode and reduction happens at the cathode. Let's write these half reactions. So over here at the cathode, we start out with Na1+. That gains an electron, plus E-, the symbol for electron, and that gives us neutral sodium, Na, without a charge. That's how we know it's neutral. Now over here at the oxidation half reaction, I'm going to write this a little bit incorrectly first, and then I'm going to fix it. Okay, so here we start out with two Cl1-, okay? Two Cl-. And then what happens is these lose two electrons, 1, 2, get pulled up to the battery. So I'm going to write minus 2E-. That's incorrect, but I'll fix it in a minute. And that gives us a molecule of Cl2 gas. Now what's wrong about this? Well, you can't subtract things in a chemical equation, even though it makes a lot of sense. So to make this correct, I have to put these two electrons on the other side of the chemical equation. So here is the correct version, where I've just moved the electrons over here. And this is the correct way to write the oxidation half reaction. Now that I've written the oxidation and reduction half reactions, I want to show you how we can put them together to get a reaction for this whole process. Now let's combine these half reactions that we just wrote. In order to add or combine these half reactions together, they have to have the same number of electrons, but they don't. Right now there's one electron here and two electrons here. So to fix that, I'm going to take this reduction half reaction and I'm just going to multiply it by 2, just like it's a math equation. And that is going to give me this new reaction. I've just put a 2 in front of everything, distributing it across the reaction. Okay, so there's my new reduction half reaction, and then here's my oxidation half reaction. Now that they have the same number of electrons, I can add them together. And this is what I get. I take everything on this side of the arrow and put it on one side. I have my Na, my 2 electrons, and my 2 Cl on this side. And then on this side, I have my Na, my Cl2, and my 2E-. Now there's still a little bit more that I have to do before this equation is totally finished. If there's anything on both sides of the arrow, we cancel it out. So there are 2 electrons here and 2 electrons here. I'll cancel those out. And then I have 2 Na plus here, and I have 2 Cl- here. I can combine those together to make NaCl. So my final equation is going to look like this. 2 NaCl, and then on this side, 2 Na plus Cl2. And you'll notice that I've also put in these parentheses to show the physical state of each of these particular compounds. This is liquid because it's so hot, it's molten. The Na is also liquid because it's so hot. And the Cl2 is gas and just floats away. So let's just pull everything together that we talked about. Here is our final equation for the electrolysis of sodium chloride. This happens because sodium gains electrons and is reduced. This happens at the cathode in the electrolytic cell, which pushes out electrons. It's where reduction takes place, and it's where sodium gains these electrons. Here is the half reaction for the reduction of sodium. Then chloride loses electrons. It undergoes oxidation, and this happens at the anode in the electrolytic cell. The anode pulls in electrons, oxidation happens there, and here is the half reaction for chloride losing electrons and getting oxidized. So that's how sodium chloride turns into sodium and chlorine gas during electrolysis. Here's another super common example, the electrolysis of water. We take water, H2O, add some electrical energy, and we get hydrogen and oxygen gas. You might be able to tell this is a balanced equation because I think you guys can handle it. Now, what's with this H2 and O2 here? Well, hydrogen and oxygen, just like chlorine, which we saw earlier, are examples of the diatomic elements. You'll never find just an H or an O alone by itself. These elements always pair up and form twos. So that's why we got H2 and O2 here. Now, this equation represents an oxidation reduction process. So electrons are moving, they're being transferred. Let's figure out how they're being transferred by looking at the oxidation numbers. I've got some rules for writing oxidation numbers here. These are just a few of them. These are just the ones that are relevant to the equation that I'm talking about here. Okay, so I've got hydrogen. Hydrogen is +1 when it's with nonmetals like oxygen. Oxygen is usually -2. And then over here, we have hydrogen and oxygen. These are elements by themselves. They're not combined with any other elements. So H2 is going to be 0 and O2 is going to be 0. Okay, so those are the oxidation numbers. And now to see how the electrons are being transferred, let's look at the change in oxidation number. Okay, starting here with hydrogen. Hydrogen is +1, and then over on this side of the equation, it is 0. So its oxidation number is going down, which means that it is undergoing reduction. It is gaining electrons. Oxygen over here is -2, and then on the right side of the equation, it is 0. So oxygen's oxidation number is going up from -2 to 0. Oxidation number going up. That means it is undergoing oxidation, which is loss of electrons. So oxygen is being oxidized. It is losing electrons here. This process is important because just like we saw in the previous example with sodium chloride, this process doesn't happen on its own. It's not spontaneous. You can have water in a glass for hundreds of years if it doesn't evaporate, and it's not going to turn into hydrogen gas and oxygen gas. It's just not going to do that on its own. So just like the previous example, we're going to have to use the electrical energy from a battery to force this process to happen. So now let's take a look at the device that we'd use to do electrolysis of water. It looks a little bit different than the device we talked about earlier because often when we do electrolysis of water, we want to be able to keep or hold on to the oxygen gas and the hydrogen gas that get produced. So this is the electrolytic cell that we'd use to do the electrolysis of water. Here's what's going on. We have a container that has water in it. And then we got these weird looking things here. What are these? Well, these are actually test tubes that are filled with water and are put upside down in the top of this container. So it's like you'd fill them with water and then you'd very carefully turn them upside down so they're still filled with water and they're in the container. Then just like in the previous example, we've got these electrodes here. The electrodes are in the test tubes. You can see that they're like sticking in the test tubes, and the electrodes are hooked up to the battery. It's the electrodes that are putting electrons into the water or pulling electrons out of the water. Okay? And then finally, of course, we have the water. Now I should say this electrolysis process doesn't just happen in distilled pure water. we got to add a little something like sulfuric acid here to allow electricity to flow through the water. So you can't just do this in pure water. Got to add what we call an electrolyte like H2SO4, sulfuric acid. Okay, now let's look at how these electrodes here are connected to the battery. Okay, this electrode here is hooked up to the negative side of the battery. So electrons, as you can see here, are moving out of the negative side and they're being pushed into this electrode. So that means that this is the cathode. It's the site of reduction. Over here, this electrode is hooked up to the positive side of the battery. So electrons are moving out of it. That means that oxidation is going to be taking place. It's going to be pulling electrons from things. And this is what we call the anode. So we've got hydrogen gas and oxygen gas. What gets made where? Well, hydrogen here in water gets reduced to form hydrogen gas. So the cathode, the site of reduction, is going to be where hydrogen gas gets produced, H2 produced here at the cathode. And then oxygen in water gets oxidized to form oxygen gas. So over here at the anode, the site of oxidation, oxygen is going to be produced. So we hook everything together, we add a little sulfuric acid to the water, connect the electrodes to the battery, and we'll start seeing bubbles. That's the gas being formed on the electrodes. And those bubbles are going to start moving up to the top of the test tubes. And if you look carefully, you see a really cool thing happen. The level of the water starts to go down because gas is flowing up, it's floating up, and it's collecting at the top of the test tubes, and it's forcing the water down. So you see the water level slowly move down as the gas collects at the top of the test tubes. It's really cool, and you can watch this. You can see this happen in the lab. Now, something else really interesting happens. You'll see what I did here, and I'm not just being careless. On the side that's producing hydrogen, you get twice as much gas as the side that's producing oxygen. There's twice as much hydrogen gas as oxygen gas. Why is that? Well, take a look at this balanced equation here, okay? We have 2 H2 and just 1 O2. So there is a 2-to-1 ratio of hydrogen gas to oxygen gas. So that means that when we do this electrolysis, we are physically going to get twice as much hydrogen gas in this test tube as we get oxygen gas over here. Okay, so that's the big picture of how we do electrolysis in the lab and what's going on here in the electrolytic cell. Now let's take a look at the half reactions for the reduction of hydrogen and the oxidation of oxygen. Let's break this process down into the two half reactions that make it up. Now let me just tell you, when it comes to writing half reactions for the electrolysis of water, there are so many different ways to do it. And it seems like every textbook or every teacher has their own way of writing these half reactions. In this video, I'm using the half reactions that I think make most sense. But if your teacher or textbook has a way they really want you to do it instead, just learn their method. Every way of writing these is essentially equivalent. They're essentially the same. They just look a little bit different. So again, I'm using the reactions that I think make most sense for this video. Let's start with a reduction of hydrogen. I really want to show you what's going on with the atoms and electrons in these half reactions. Okay, so we start with 2 molecules of water, H2O, and you'll see that I've written the oxidation numbers above each of the atoms. So in the reduction of hydrogen, essentially what happens is it's like we take 1 hydrogen from each of these water molecules and pull them off, and then we combine them to make a molecule of H2, hydrogen gas. Now what has to happen with the electrons for this to take place? Well, each of the hydrogens over here has an oxidation number of +1, but then they have an oxidation number of 0 over here. So that means that each of these hydrogens has to gain 1 electron so that its oxidation number can be bumped up by 1. Okay, here's a diagram sort of showing what's happening here. Okay, this hydrogen was plus 1, and then it gains an electron and becomes 0. This hydrogen was plus 1, and it gained an electron and became 0. Where do these electrons come from in the electrolytic cell? Well, they came from the cathode, because the cathode is what pushes out electrons. The cathode is where reduction happens. Okay, so we get one molecule of H2, but then we have these parts of the water molecule which are just left behind. So we get an O and an H, and these two things together have a negative charge of 1 minus. These are polyatomic ions, are called a hydroxide ion. And the reason why they have a charge here is because notice that their oxidation numbers haven't changed, because we're not adding or removing electrons from the rest of the water molecule. So these numbers are just staying the same as they were over here. You add these oxidation numbers up and you get minus 1, minus 1. So that's the charge of this ion. Okay, so this is how the reduction happens with pictures. Let's look at how we can actually write an equation, actual half reaction for what's going on here. We start with 2 molecules of H2O, and then we gain 2 electrons, so plus 2E minus, and that gives us 1 molecule of H2, and then we get 2 OH minuses. So that's the half reaction here. That's a half reaction for the reduction of hydrogen. Now let's take a look at the half reaction for the oxidation of oxygen, okay? Just like up here, we start with 2 molecules of H2O. And for the oxidation of oxygen, it's going to be like we pull off these 2 oxygen atoms to make a molecule of O2 oxygen gas. Now, how about the electrons in this case? Well, both of these oxygens were minus 2 for their oxidation number over here, and then they became 0 over here. So each one of them has to lose 2 electrons to become 0. This one was minus 2, then it loses 2 electrons, becomes 0. This one was minus 2, it lost 2 electrons to bump its oxidation number up. It's losing electrons to 0. So that's what's going on here. Now, where are these electrons going? Well, the electrons are going to the anode, because it's the anode in oxidation reduction reactions that is pulling in electrons. Okay, so this is what's happening with the oxygen. What about the rest of this? Well, we have 4 hydrogens left over after we pull off those oxygens, and their oxidation numbers are not changing because we're not adding or removing electrons. So we're just going to get 4 H pluses over here left over that have an oxidation number of plus 1 because that's not changing. Let's do the same thing that we did up here. Let's write a half reaction for the process. This is a little bit more challenging. As before, I'm going to write it incorrectly first, and then we're going to fix it. Okay, so we start with 2 H2O, and then we lose 4 electrons. Minus 2, so minus 4 electrons. And that gives us O2 plus 4 H plus, these up here. Now, as you probably know, we can't use the subtraction sign in a chemical equation. So we have to make this 4 electrons and put it over here. So this is what we're going to get instead. We just move this 4 electrons over here, 4E minus, and there we go. Okay, there we go. Now we can see it. And these are the half reactions for the reduction of hydrogen and the oxidation of oxygen. Now let's combine them, put them together. Okay, now so for combining these half reactions, we want them to have the same number of electrons. The reduction half reaction that only has 2 electrons, we have 4 here. So the way we're going to solve this is we're going to take this whole equation and we're going to multiply it by 2. And distributing this 2 across the equation, we are going to end up with this: 4H2O, 4 electrons, 2H2, and 4 OH minus. So that is our new reduction half reaction. Now we can take these 2 half reactions and add them together. We're going to get this, We take everything from this side of the equation and put it here, 4H2O, 4E minus, 2H2O. Then we have our arrow, and then we have 2H2, 4OH minus, O2 plus 4H plus 4E minus. All right, now there are a few things that we can do here. If something appears on both sides of the arrow here, we can cancel it out. Okay, so we'll get rid of this one and we'll get rid of this one. But that's not all we can do. Look at this. We have 4OH minus here and we have 4H plus. OH minus and H plus combine to make water. Now also, look at this. We have 4H2O here and 2H2O here. So we can combine these to get 6H2O. All right? So here's how we can rewrite it. We pull these together and get 6H2O. We get rid of the electrons there. And then we have 2H2. We combine 4OH minus and 4H plus to get 4H2O. And then we have our oxygen. But you know what? There's actually one more thing we can do, because look, we have H2O on both sides of the equation. So I can subtract it so we can get rid of it from one side. I'm going to do minus 4H2O here. I'm going to do minus 4H2O here. That's completely going to get rid of the H2O on this side, and it's going to leave me with 6 minus 4, 2H2O on this side. Here is the same balanced equation that we used when we started. You put the half reactions together, and this is what you get. So that is the electrolysis of water. Hydrogen is reduced, it gains electrons, this happens at the cathode, the site of reduction, and H2 is produced there. Then oxygen is oxidized, it loses electrons, this happens at the anode, the site of oxidation, where the oxygen is produced. We got these two electrodes in these upside down test tubes, and the gas, the hydrogen and oxygen, collects at the top. And we've seen that we get twice as much hydrogen gas as oxygen. And that's just because in our balanced chemical equation, there's a ratio of 2 hydrogens to 1 oxygen. So that is why we get twice as much hydrogen here as oxygen here. So that's how electrolysis works. That's how you put electrical energy into a chemical reaction to make something happen that wouldn't happen otherwise. Something like taking sodium chloride and breaking it apart into sodium metal and chlorine gas, or something like taking water and splitting it apart into hydrogen gas and oxygen gas.